All right, well, welcome everyone. I am JJ. Let's tackle an example problem. We have a couple here. Remember, a couple is just a pair of equal and opposite forces. They are parallel to each other, which has to be true for them to be opposite. And they both have 450 Newton forces on here. They are equal and opposite. This is a couple. Let's determine the resultant couple moment that these will cause. So replace this with a couple moment, basically. Then we're going to show that on a quick sketch to work through that. Anytime we're dealing with couples, we should, just like with regular moments, we're going to break things into x and y components. But rather than saying what's our rotation about a given point, like at point A in here, we're just going to do what's our distance in between the pair of forces. So we'll work with our x components and our y components. Let's sketch in those y components really quick. I really have over here some y component going down. On this side, some y component coming up. Those are also equal and opposite in here. To get the couple moment, I just want our force times our distance in between these, that perpendicular distance. So we're going to write this out to come in and solve this. We'll say with positive going counterclockwise, we're summing up our couple moments. That C is for couple moments in this one, rather than point C. It looks the exact same. We're just going to have to figure out a way to keep that straight. But summing up our couple moments. So we have for one of these, a force that goes down, one that goes up. When we check our rotation direction on that, we're just going to want to, there's multiple ways we could do this, but I would say my main way is, if I'm working this on paper, I would physically pull down on the arrow that points down and push up on the one that pushes up, or points up. And my whole paper would start to rotate counterclockwise, which means it'd show up in there as positive. I could also come in and try to connect my circles in there. My arrow here pointed down, so if I drew a circle that started going down and connected into the tail of my arrow over here, I have to go to the bottom and come up, connecting back in again. I'm drawing a counterclockwise circle in here, going counterclockwise with that. It is positive. Either way, we should be able to get to that same kind of end point in there. To me, getting down to being able to spin our paper ends up working a lot quicker in general for everything. Than trying to draw circles on all the time. But either way, will get us there. Let's come in and just keep going with that. So we have our rotation direction. This should be equal to, I need force times distance. My force is just the y component of these. It doesn't matter if I say that acts up or this one acts down, because we're looking at moment, and we already established this will be counterclockwise. So our y component is just 450 sine 30. Times, I need a distance. What's my perpendicular distance between the y component over here's line of action and this one? Basically between my hands here. We should be getting that is, I'm not directly given that, but if I try to measure from one to the other, I know from the bottom one, it's 300 millimeters over to get to the left edge of my object. And then if I come back 100 millimeters, that difference in there, 300 minus 100 will give me my distance. So times 300 minus 100. That's my y component times an x distance in here. Still tackling moment, it's just now between two components of force. Then we can repeat that exact same process for our x components in here. If we erase what we drew for the y terms and come in and try that for those x terms. I have an x component on the top that points to the left. On the bottom, that's pointing to the right. And again, with those two methods that we just laid out, if I just on a piece of paper pulled at the top, if I pull it to the left, because my arrow points to the left, and at the bottom, pull it to the right, my entire paper should spin counterclockwise. So we'd be adding this in. We'll go ahead and add that plus in now. Or we could come through and try to do the connecting the arrow step in here. If I drew that in, I would be connecting. I'm going to draw along one of my arrows, or at the top going to the left, so I can hit the tail of the other one, and then connect back in. And I'm again drawing a counterclockwise circle. Either way, I'm really getting that same, what's my direction, and point in here. Those are my two methods that I use. Figuring out moments are a struggle. Look back at earlier videos and review moments, or find something online. This is critically important for us in statics to be able to get a moment rotation direction. Let's get you there. But we know we're adding in because we checked our rotation direction. So plus, we need our x component of force. That'd be 450 cosine of our angle, cosine 30, times, now I need a y distance on this. So from the x component down here up to the x component on the top, just that perpendicular distance between their lines of action, so that straight line point on both of them, and just my total height, times 250. Or that's going to get me that this is 1,400 or 142,425 Newton millimeters. And it went counterclockwise. Our other option, though, could be to say, let's convert that. Instead of Newton millimeters, we might want to use Newton meters. We'll say that our total moment about point C is, just dividing by 1,000, 142.5 Newton meters, and it went counterclockwise. Counterclockwise. And that would be our final answer for our problem, or for that piece of it. We're also asked, show it on a sketch. Really, that entire intent there is to reinforce, if we sketch our object in here, our couple moment, I can show this anywhere. It's going to cause that same tendency to rotate no matter where it's shown on here. So if we're looking at an entire object, I can stick this anywhere on here and my answer would be correct. So I'll show it in the corner there. And this is 142.5 Newton meters. The location doesn't matter for us when we're looking at that whole object. Later, as we move through our course here, we'll start looking at what if we have multiple members connected together, and then we need to say just don't move it off of the member. And eventually we'll start looking inside of the object, what's going on internally, and then we'll say just don't move anything at all. But for right now, we're just saying how does this entire object tend to rotate? We could put that couple moment anywhere. Our force times distance type step when we sum up moments. If we have a couple moment on something, we're summing moments, we just stick it in. We don't need to multiply by a distance because location is irrelevant for us. We'll go ahead and wrap up there. Hopefully this is a useful video for you. If it was, hit those like and subscribe buttons. Let's get you an A with JJ.